All right, this next unit we're going to talk about is going to be all about radicals and rational expressions, as well as radical or rational equations. So to begin with, we want to just talk about our basics. So we're going to talk about how we can convert back and forth between radicals. So something like a square root. We will not deal exclusively with square roots. We'll also look at cube roots, fourth roots, fifth roots. We can look at whatever root we want, and rational exponents. So looking here, just so you're familiar with some terminology that you'll hear me use, this number up here used to indicate the root. That's called the index. This number here, you're probably familiar with this, is my exponent, is the power that my variable or my number is being raised to. And the thing that is being raised to the power is called my base. So when we are converting back and forth between forms, it's important to know that our index is always going to be the denominator when we go to exponential form. So once again, as I said, the index will become the denominator because exponential form, notice it's rational exponents, rational meaning a number that can be written as a fraction. So we're going to be going to exponential form with fractions. So the index will be the denominator. I probably can't write small enough to fit it in the screen here, so I apologize if you can't read that. It does, or it is supposed to say denominator. The exponent is going to become, or is going to become my numerator when in exponential form, and my base will remain my base. So let's look exactly what I mean by looking at these couple examples here. So notice here I'm in radical form. It's a radical because it has a root. In this particular case, it's a square root. Because square roots are the most common and occur all the time, we often do not write the index with the square root. So if you see there is no index, it means it is the square root, square meaning the second root, so we are going to go ahead and use 2 as the denominator when we change to exponential form. So rewriting this in exponential form, I see that my exponent is going to become my numerator. Well, if there is no exponent written, it means it's a 1, so I'm going to go ahead and write this as 1 over 2, and I get x to the 1/2. If I do the same thing with example 2, again, I do not have any kind of index, so if I don't have an index, I know that it means that my index is a 2, so my denominator will become 2. In this case, I currently have an exponent of 5, so my exponent will become my numerator. My base is x, my base stays the same, and I get x to the 5 over 2. Looking at my third example, so notice that my index is 3, so when I change this to exponential form, I will keep the same base of x. My denominator will be 3. This is called the third root. And my exponent is 4, so it will stay as a 4 in my numerator, giving me x to the 4 over 3. In exponential form. One thing I want to point out, which you'll realize as we continue through this unit, these are not necessarily in simplest form. I am not worried about simplifying right now. I am just worried about changing forms. So if at any point you go back and rewatch this after you've learned how to simplify them and you're saying these aren't simplified, you're right, they're not. Looking at the next one, example 4, so if I draw some lines here to make it a little bit more clear. Example 4. Again, all I want to do is convert to exponential form. I have x to the 11th underneath the 4th root. So my base is x. My base will remain x. The exponent is 11, so that will be my numerator. The 4 is my index, so that will become my denominator. And I get x to the 11 over 4. And I do apologize because my writing is pretty big. These are exponents. They almost look like they're just being multiplied. They should be little exponents. Looking at the next one and the last one here, I see that I have x to the 6 underneath the third root. So my base is x. So my base, when I write this, will remain x. My numerator or my exponent is 6. My denominator or my exponent is 3. So I do get x to the 6 over 3. I am aware that that can be reduced. Again, right now my goal isn't to get it in simplest form. My goal is just to change forms. That is how I'm going to go ahead and change between radical form and exponential form. So a big thing to remember, is that the index is the numerator, the index is the denominator, and the exponent is the numerator. So exponent of 1, numerator of 1. Exponent of 5, numerator of 5. Exponent of 4, numerator of 4. Exponent of 11, numerator of 11. Exponent of 6, numerator of 6. Index of 2, because 2's aren't written, denominator 2. Index 2, denominator 2. Index 3, denominator 3. Index 4, denominator 4. Index 3, denominator 3. Moving on to look at how we can use this with numbers. So if I want to simplify numbers with an exponent and a root, one thing to point out is that order does not matter. You can either take the root first, or you can raise it to the power first, or use the exponent first. So let me show you what I mean on these examples. So if I look at 9 to the 3 over 2, this can be either written as the square root of 9 cubed, or it can be written as 9 cubed underneath the square root. Order does not matter. I can either do the exponent first, like I did in this one, or I can do the root first, like I did here. You'll get the same answer either way. Pick whichever one works better for mental math. Well, I know that the square root of 9 is 3. That's really easy for me to do in my head. This here. Doing 9 cubed in my head isn't as easy for me. So for that reason, I'm going to choose to simplify this one. So simplifying that one there, the square root of 9 is 3. The cube drops down because I haven't done anything with that. 3 cubed I know is 27. So 9 to the 3 over 2 is just 27. Again, I would have gotten the same answer had I taken and done 9 cubed, could have used my calculator for assistance, and then taken the square root of that number. Looking at the next one, I have 8 to the 2/3. So again, I can take the cube root first, I can do the denominator first, and then square it, or I can square it and then take the cube root, thus using the exponent or the numerator first. So again, pick what it's easier to do with mental math. So I know that the cube root of 8 is 2 because I'm fairly familiar with my cube roots. I also know that 8 squared is 64. So in this one, I don't think it really matters. So just to show you can do it both ways. If I do the first way, if I look at the first way it's written here first, it tells me to first take the cube root and I get 2, since 2 times 2 times 2 is 8. My square drops down and I get 4 for my final answer. If I do where I take the square first, 8 squared is 64. Again, I am fairly familiar with my cubes, so I know off the top of my head that the cube root of 64 is 4. So notice I do get the same result either way. And looking at 2 more examples to finish up here. My third example, I have 5 squared over 3, so 5 to the 2/3. So I can either use that denominator of 3 to take first my root and then square it, or I can square the 5 using the numerator and then take the cube root of it. So it doesn't really matter which one I do, which is easier mental math. I have no idea what the cube root of 5 is. It's going to be some crazy decimal. So I don't think I'm going to follow this one. I think I'm going to go ahead and follow this setup instead. 5 squared gives me 25, so that gives me the cube root of 25. I asked myself, are there any perfect cubes in 25? Well, I think about my cubes, and I know that 8 is a perfect cube since 2 cubed is 8. 27 is a perfect cube since 3 cubed is 27. This cannot be divided by 8 or 27. There's no reason to go higher because I know it can't be divided by a number higher than itself. So this would be my simplest form on this. Looking at example 4, my final example, I see I have 8 to the 3 over 2, so I can use the denominator first and take the square root of 8 and then cube it. Or I can cube it first, taking the numerator, and then take its square root. I don't know what the square root of 8 is. It's not a perfect square. I know I could simplify it, but since I don't specifically know what number corresponds with the square root of 8, it'll be some crazy decimal. I'm going to actually go ahead and not use this version, but use this version. So I'm going to first cube 8, So I know that 8 cubes means 8 times 8 times 8, not 8 times 3. So 8 times 8 gives me 64. 64 times 8 gives me 512. So I've taken care of the cube. I have done nothing with the square root yet. So 512 I know can be divided by 16. So I do want to simplify it. So remember on this one over here, I could not simplify that because 25 did not have any perfect cubes. 512, however, does have perfect squares in it, so I do want to do that. Make some more room here. 512 I know can be divided by 36, so I'm going to say this is the same thing as 36, or excuse me, I know it can be divided by 16. This is the same thing as 6 squared root of 16 times the square root of 32. Well, I know that the square root of 16 is 4. I also know that I have not taken all of my perfect squares out, because 32 I know is 2 times 16, so this can be reduced further. So I'm going to do that in my next step. So the 4 will stay out front. 32 is going to become the square root of 16 times the square root of 2. Well, 4 and the square root of 16 are written right next to each other, so I do know that that's multiplication there. So I will get 4 times 4 times the square root of 2, giving me a final answer of 16 square root of 2. I ran out of room underneath. And that is how you can A, convert between radical and exponential form, and B, use those concepts or use that idea to simplify a number being raised to a rational exponent.